All right, we ended the last video clip, which was on part one of events, clocks, and observers. We are talking about a lattice or a grid of clocks that we're going to use to specify when something happens. Not only when, but where. So a clock, we'll have a clock at every location in space, say 3 dimensions, and then using a photo device, whenever an event occurs at that location, photo will be taken that records not only the location of the event in XYZ coordinates, but also the time on the clock at that location. But it raises the question of how do we synchronize the clocks? How do we make sure they're synchronized? And so that's what we're going to work on in this video clip. We've reduced it just to 1 dimension now. As I mentioned last time, we did 3 dimensions last time just to get the general concept. From now on, we'll be working in 1 dimension. So we just have the x-axis here. So anything that occurs can only occur along the x-axis, along this line, any event that occurs, say a flash of light. And so here's an example of a lattice or a grid of clocks along the x-axis. So at each point along the x-axis, I have a clock. Clearly, if I want to specify like halves and tenths and things like that, I just imagine I have a clock at every given tick mark, say, on our x-axis. Here's the origin. Here is the observer. We'll just imagine it's us standing there. We're going to be observing things. And so then here's our grid of clocks. I also mentioned, by the way, in the last video clip that there are 2 different ways of doing this. And actually, we didn't quite get to those 2 different ways in the last video clip. And this video clip, we will talk about those 2 different ways. So if you're wondering what happened to that, this is what's coming up here. So the challenge is how to synchronize those clocks. And so here we are, we're the observer. We have a whole bunch of clocks, and we need to get them at each point along our x-axis, and we need to make sure they're synchronized. So first we'll assume we have a master clock. And by the way, hopefully you did the thought experiment, sort of the priming the brain experiment in terms of thinking about how you might do this, because actually, even though you might think, again, this seems sort of trivial, this was one of the fundamental insights of Einstein that led him to the special theory of relativity, that there were challenges with synchronizing clocks, and it wasn't quite as obvious and straightforward as one might seem. And in fact, this is a case where this was not just some esoteric thought experiment Einstein was doing. These were problems that came out of the electro-technological context of the day, that it was very important as railroads expanded. As railroad expanded, you need to have good timekeeping systems so that every city had more or less the same time, and you had to make sure your clocks were synchronized between various stations and so on and so forth. And there were a lot of patents and inventions, I should say a lot of inventions, that then people submitted patents for at places like the Swiss Patent Office where Einstein was working. So he clearly was getting a lot of this, not only just from sort of thinking about esoteric abstract matters of how do you synchronize clocks, but from the technology of the day. It was a key issue that people were trying to solve in various ways. So, whole idea of how do we synchronize these clocks. One way, perhaps, could be we'll have a master clock, say here, that the observer has, and the observer will bring all the clocks together in one place and set them according to the master clock, so everything's running just fine, they're all identical clocks, and then move them out along the x-axis at that point. And so that when something occurs, a flash of light occurs over here, and it records it in a photograph, then the observer can be confident that it was the correct time, and this clock is synchronized to the master clock here at the origin. What Einstein came to realize, though, and again later on in the course we'll get into a few more details of this, is that when you actually move a clock, you can't be guaranteed it remains in sync with the original clock. And so even though that method seems like it should work just fine, bring them all together to one master clock, they're all identical, they're all running properly, synchronize them all, and then move them out along to wherever they need to be. In actual fact, it has some potential problems with that, where things will get unsynchronized as soon as you start moving them. Now, what you could say is that we will, move them as slowly as we want, such that if there is any unsynchronization, desynchronization that occurs, it's going to be small enough that we won't care about it. So there are ways to get around this, but we're going to use a different method. So this is the first method that, in principle, could work if you're really careful about it, but we're going to use a different method. And this method is, at least we're going to use a different method in principle here. This method is, let's put all the clocks out there, but we won't have them running yet. Okay? We'll just have our master clock here, put all the clocks along, and the idea is that at time t equals 0, we'll have a light pulse be sent along in both directions. So we'll just say, we'll use orange here for a light pulse again. So I guess we used green last time, so we'll use orange this time. So here's the light pulse sent out from the master clock position at t equals 0. Okay? And then as the light pulse goes along my line of clocks here, when a given clock receives that light pulse, or when the light pulse goes by and that given clock is triggered by the light pulse, it will start running. But then you say, well, if this starts at 0 and sends the light pulse out, and then this one starts running when it receives the light pulse, it's going to be behind this clock clearly. So we're going to get around that. We're going to say, okay, if this clock here is 4 units away, whatever units we happen to be using, miles, kilometers, meters, whatever, we know how long it takes light to get there. So we'll say, okay, clock number 4 here, or clock at position 4, we're going to set it ahead just the amount of time we know that the light pulse takes to get from 0 to 4. Now let's just imagine it's 3 seconds. Okay, so it's pretty far away here, obviously, at the speed of light. But we'll say, okay, we know that the light pulse, we know what this distance is, we know how fast the light will travel, and we know that it will take 3 seconds to get to that position there. And so we will set this clock 3 seconds ahead, so that the light pulse goes off here at 0, t equals 0. It's going along here. When it reaches this clock, 3 seconds have elapsed, and if we set this clock 3 seconds ahead, it's not running at this point. When the light pulse reaches it, it will trigger the clock to run, and it will start running at 3 seconds. And then maybe this clock here is, up here, let's see if that would actually be 8 here, 6 seconds ahead. So when the light pulse reaches here, it would have taken 6 seconds from the origin to get there from our master clock, and therefore it would be set 6 seconds ahead, and when the light pulse reached it, it would trigger it and start running. And then everything, assuming we did that with all the clocks, everything would be synchronized. We don't have to worry about any problems with moving the clocks around. All we have to know is what the speed of light is and then how far away each clock is from my master clock. So that's the idea of how we could synchronize our clocks in theory. Obviously, we're just doing all this as thought experiments, but that's a method we can use to make sure all our clocks are synchronized, and so that for the observer here, once they have their lattice of clocks, they can be assured that any event that occurs, we'll use green this time, so say some event occurs right here, flash of green light, and so we know the position along the x-axis is at x equals 7. The clock will record the time of the flash, and then the observer later on can go out and look at that clock and say, oh, okay, look at the photograph there and say the flash was recorded at x equals 7 at t equals 3.8 seconds or something like that. And so again, that's the idea of events, clocks, and observers and how they all fit together and what it means to make an observation. So from now on, when we say somebody observed something, observed an event to occur, what we mean is if we're using just the x-axis here, it's the x location of it and the time recorded on that photo that is taken at that instant in time. So again, the photo clock principle or the clock principle is what we're basing this on. And we're assuming we can synchronize all the clocks by sending out the pulse of light, as long as in advance of that we have set each clock ahead just the proper amount, so when the pulse of light reaches it and it starts running, then they're all synchronized with each other that way. Okay, so events, clocks, and observers. And in the next video clip, what we're going to do is look at a different way to visualize how events occur and something called space-time diagrams, which we'll find will be very useful for visualizing some of the concepts in the special theory of relativity.